Hello guys, you are welcome to JAMB 41's YouTube channel. So in this video lesson, I would like us to look at an aspect of gas laws. We're going to deal with Graham's law of diffusion. In the course of this class, I am going to derive this Graham's law of diffusion in terms of its mathematical equation, which is necessary for use in solving certain gas parameters as I encountered in the study of gas laws. Before we move on into this concept of Graham's law of diffusion, I would like to give you this little update about the JAMB 41's 2025-2026 lesson, which is in progress already. WAEC and JAMB lesson at Integral Development Consult IDK. So guys, today we dealt with this aspect of chemistry. We studied how the knowledge of valency can be used to write the correct chemical formulae of a given compound. You know what? As a science student who must deal with the concept of chemistry, being able to write the correct chemical formula of a given compound is fundamental. Of course, you don't joke with it. So in our class today, we did wonderful work on it. We were able to write out 10 different chemical formula correctly using the knowledge of valency, to do that. So I'm using this opportunity once again to inform the public that our lesson is in progress. If you know you're sitting for WAEC, alright, and JAMB next session, make sure that you contact us as soon as you can in order to take part in this lesson so as to be coached rightly and for you to prepare for the next JAMB to be sure that you are able to score the required points. Alright, remember too that you can join us online in our classes. If, for example, you are not in Oka, Anambra State, okay, you can actually contact us to join the JAMB 41 online classes. To do this, you have to become a channel member. Just below this video lesson, you will see the Join tab. If you tap it, the packages available on JAMB 41 will display. Select the package that is convenient for you to become the JAMB 41's channel member, so as to follow through as we coach you for these professional exams soon to kick off. Alright, so let us get to business. We are going to look at the concept of Graham's law of diffusion. First of all, we want to answer the question, what does this law study? What does it study? You're dealing with the law. You want to know the aspect of gas parameters that Graham's law of diffusion deals with. And I'm going to tell you, okay, Graham's law of diffusion studies the rate of diffusion of a gas with its relationship to the molecular weight of the gas or the density of the gas. In fact, we can also link it to the time it takes the gas to diffuse. So you see, when dealing with Graham's law of diffusion, you are interested in the rate of diffusion, you are interested in linking that rate of diffusion to the density of the gas, to the molecular weight of the gas, as well as the time it takes the gas to diffuse. I'm going to give you a quick example. If you open two perfumes, say at this point, if you open two perfumes at this point, you see, there's something that usually happens. If you are at that point and maybe the gas, perfume is a gas, it diffuses. If this perfume diffuses from the gas container, sometimes you notice that one of the gases, the aroma will be perceived before the other one. And that simply tells us that this gas, the speed with which it travels is faster than the other. Let us assume you have gas A and gas B. And it happens that you perceive gas A first before perceiving gas B, when these gases are being opened. This simply means that gas A travels faster than what? Gas B. So the relationship between this rate of diffusion and maybe the gas density, molecular weight, and time is what we're interested in dealing with in this video lesson. We start first by stating Graham's law of diffusion. Graham's law of diffusion states that The rate of diffusion is inversely proportional to the square root of the density of the gas if temperature and pressure are kept what? Constant. Having stated this law, I would want to draw your attention to the relationship between gas density and the molecular weight of the gas. Relationship between gas density and the molecular weight of what? A gas. The density of the gas is directly proportional to the molecular weight. What does that mean? If the molecular weight of a gas increases, the density will also increase. So you want to take note of this point. This simply means that if, according to Graham's law of diffusion, the rate of diffusion is inversely proportional to the square root of the gas density, we could also relate the rate of diffusion of a gas is also inversely proportional to the square root of the molecular weight of the gas. So these points are very important for us to take note of. You see, rate of diffusion inversely proportional to square root of density, also inversely proportional to square root of the molecular weight of the gas. Now that we've stated Graham's law of diffusion, we are now going to see how we can derive the mathematical expression for calculation purposes when studying Graham's law of diffusion. Please come along as I derive these equations on the board, okay? Alright, so we are going to move on to derive Graham's law of diffusion equation. Remember, rate of diffusion, I am going to use small letter r for the rate of diffusion. And based on the law stated already, the rate of diffusion is going to be inversely proportional to the square root of the density of the gas. Now, permit me to use d to represent the density of what? The gas. We also said that that rate of diffusion can still be written to be inversely proportional to the square root of the molecular weight of the gas. Permit me to use capital M as the square, that's the molecular weight of the gas. So either of these can be used to generate the rate of diffusion. Now observe, if I proceed to remove this sign of proportionality, I'm going to get rate of diffusion to be K divided by square root of what? D. In the same way, we can write similar equation as R equal to K all over square root of capital M, alright, which is the molecular weight. So this is the concept of the rate of diffusion. But there is something about rate of diffusion that I would like you to know. If I want to study the rate of diffusion of gas, we usually approach it comparatively. What do I mean by that? You compare the rate of diffusion of one gas to the rate of diffusion of another gas. So that will help us to know, okay, these two gases, which one will diffuse faster? Alright? Which one will have its quantity move faster from where it is highly concentrated to where it is low in concentration. The whole idea here is simple. In studying rate of diffusion of a gas, we compare two gases in that case. If that is the case, I am going to assume that we have gas A and gas B, or you can say gas 1 and gas 2. The choice is yours, but let me use A and B. Is that okay? If I have gas A, the rate of diffusion of gas A to be R subscript A, then it's going to be equal to this constant divided by the square root of D, where D is the gas density. Now I want to compare this rate of diffusion of this gas with another gas. I'm going to assume the other gas to be B. So if I take this as equation 1, the second gas, if I call it gas B, the rate of diffusion of that gas is going to be equal to K all over this density plus D will be dA, you know, because it is density of gas A, whose rate we just wrote in equation 1. Then this is going to be the second case for gas B. Rate of diffusion of gas B is going to be this constant of proportionality K divided by square root of the density of gas B. Now this we are going to take as equation 2. It is now time for us to compare the rate of diffusion of these two gases. We're going to compare the rate of diffusion of these two gases. In comparing it, we are going to take a divisional relationship. Now watch what I do here. I am going to take rate of diffusion of gas A over rate of diffusion of gas B, and that is going to be equal to the constant of proportionality there for gas A. Look at it, divided by the square root of density of gas A. And then remember, the rate of gas A is being divided by the rate of gas B. The rate of gas B is going to be K divided by square root of density of gas B. So we are going to solve this mathematically. If we solve this mathematically, this is going to give us the rate of diffusion of gas A to the rate of diffusion of gas B is going to be equal to, please look at this mathematics here. Remember, the numerator, as you can see, is a fraction. The denominator, as you can see, is a fraction. Division of fraction is very simple, okay? Keep the numerator constant exactly the way it is. Change this division sign to multiplication, and then inverse on the denominator fraction upside down. Okay? The mathematics, like I said, is simple here. In this case, you see the denominator of this numerator fraction. It's going to step down. And then the denominator of this denominator fraction, which is square root of density of gas B, will do what? Go up. So mathematically we have, so you see that the constant of proportionality K is the same in both cases. So what do? We just cancel them out, and then we will obtain that the rate of diffusion of gas A with respect to the rate of diffusion of gas B is now equal to square root of the density of gas B divided by square root of the density of gas A. You know, one can write this using one square root to cover that. Okay, so implies then therefore rate of diffusion of gas A to gas B will now be equal to, I want to use one square root to cover here, since you know that square root distributes over division and multiplication. So using one square root is going to be, we're going to call this equation 3. I will asterisk it because this is one equation used for solving the rate of diffusion of a given gas. You use this equation when the rate of diffusion is given to you and the density of the gas is also known. Whereby maybe one of them, you have to find it. Alright, I hope you understand this concept, right? We are going to link this rate of diffusion now to the molecular weight of the gas. Remember, I stated that density of a substance is directly proportional to the molecular weight of that substance. The higher the density of any given substance, the higher the molecular weight. The lower the density of a substance, the lower the molecular weight. So there is this direct relationship between them. It therefore means that instead of using density in this case, we can use molecular weight. So let me write it. You could also have the formula as rate of diffusion of gas A over rate of diffusion of gas B equal to square root molecular weight of gas B divided by molecular weight of gas A. Let me give this equation 3 asterisk for calculation purpose. This equation is used in the case where the examiner draws the attention to the molecular weight of the gases. You need to take note of something here, that the rate of any of the gas is actually inversely proportional to the square root of its density, or inversely proportional to the square root of its molecular weight, which is in line with Graham's law of diffusion, that the rate of diffusion is inversely proportional to square root of either the gas density or the molecular weight of the gas. Take note, rate of diffusion of gas A here is the numerator. What can you see here on the right hand side? It is denominator. Rate of diffusion of gas B here is denominator. What can you see about the square root of the density? It is numerator here. So you see there is this inverse relationship, okay? And I've established two fundamental formulas you need for calculation when treating Graham's law of diffusion. Do you have any question? If you don't have any question, remember you can always make use of the comment box below this video lesson to ask a question. And of course, the GMAT 41 will be there to respond. Alright? So you are expected to memorize this equation 3 asterisks and 4 asterisks for calculation purpose. But I'm not done yet. I'm not done. I want us to go to the foundational definition of rate of diffusion. You know, this equation that I established, 3 asterisks and 4 asterisks, is in terms of Graham's law. What about the definition of rate of diffusion directly? What are you expected to know about that? So I am going to define the rate of diffusion of the gas. Take note. I am defining the rate of diffusion of the gas. The rate of diffusion of gas is defined as the volume of that gas that flows through a given section in a particular time. Once again, the rate of diffusion of any gas is the volume of that gas which flows through a given section in a particular time. From that definition of rate of diffusion, we can also write a mathematical equation for it. Are you aware of that? Remember that rate in that definition links volume of the gas to the time it takes the gas to diffuse. And so mathematically, I can also write that rate of diffusion is equal to volume over what? Time. You want to take note of that. Rate of diffusion is equal to volume over what? Time. Let's call this equation 5. You see, an examiner can give you the volume of the gas, give you the time it took the gas to diffuse, and request that you calculate the rate of diffusion. In that case, the rate of diffusion is simply volume divided by time. I will have to asterisk this equation because you need it for calculation purposes as well too. Imagine that the volume of the gas flowing through a given time, say the volume is 20 cubic centimeter, and the time it took the gas to flow is 5 seconds. The rate of diffusion of that gas is going to be 20 over 5, which is equal to 4 cubic centimeter per second. Cubic centimeter per second is the unit of rate of diffusion. Either cubic centimeter, and remember it is volume over time. So unit over volume over unit over what? Time. It could also be in cubic meter per second, where in that case the volume will have the unit in meter cube. So in either way, anyway, you want to take note of that. Unit of rate of diffusion is unit of volume divided by the unit of what? Time. Now this is a definition given for rate of diffusion. Since we say that in dealing with rate of diffusion, we actually compare, we compare two gases. We are going to write an equation for rate of diffusion in terms of gas A and in terms of gas what? B. Just like we did to obtain the equation 3 asterisks and 4 asterisks. Are you ready for that? Please come along, let us treat that. I want to write the equation for the rate of diffusion of gas A. That is going to be volume of A divided by time it took A to diffuse. I also want to write the rate of diffusion equation for gas B. It's going to be volume it took B to diffuse divided by the time it took B to diffuse. Since we want to compare the rate of diffusion of gas A to that of gas B, we are going to present these two equations now in ratio format. Please follow along as I do that. Rate of diffusion of gas A divided by rate of diffusion of gas B is going to be volume of A divided by the time it took A to diffuse. Please watch something. If I divide this thing all over volume of gas B divided by the time it took B to diffuse, mathematically that time of B will go up, then divided by volume of B. This multiplication sign, I've used dot for it. Now, I want to tell you something. Pay attention, you can put it down. When carrying out this experiment to compare the rate of diffusion of one gas to another gas, for you to be experimentally accurate and consistent, the volume of the two gases must be the same. I repeat, the volume of the two gases must be what? The same. So that your experimental result will be accurate. You are trying to consider how fast, gas A will diffuse compared to gas B. You must use the same volume. Am I communicating? You must use what? The same volume. Then you now check which one will diffuse faster. Which one will take maybe lesser time or more time to diffuse from one point to another. So for that reason, these volumes they are the same. VA is equal to VB. If VA is equal to VB, it has to cancel out from the equation. And then you will see that the rate of diffusion RA all over RB will now be equal to the time it took B to diffuse divided by the time it took A to diffuse. I hope you understand and appreciate this, right? So this is another equation which relates, it relates the rate of diffusion to the time it will take the gas to diffuse. And so I'm going to call this equation 6 asterisks. I'm going to call this equation 6 asterisks. Now you want to watch this equation 6 asterisks, and then let us try to compare it with equation 3 asterisks and 4 asterisks. If you look at when we are writing the rate of diffusion formula here, you observe that the time does not have square roots. The time does not have square roots. But in the case of 3 asterisks and equation 4 asterisks, the density and the molecular weight, they have square roots. So you want to watch this difference, Having established this difference that you have to take note of, I would want to state also that the rate of diffusion is inversely proportional to what? Time. Rate of gas A, numerator here, time of gas A, denominator here, rate of gas B, denominator here, time of gas B, numerator here. It simply tells us that rate of diffusion is also inversely proportional to the time of diffusion. Are you getting? Rate of diffusion is inversely proportional to time. Take note of that. All said and done, as I summarize this, you want to remember that the rate of diffusion of any gas is inversely proportional to the density, the molecular weight, the time. The only difference is that if you are dealing with density and molecular weight, rate of diffusion will be inversely proportional to the square root of the density or inversely proportional to the square root of the molecular weight. But when you are studying rate of diffusion with respect to time, rate of diffusion is simply inversely proportional to time. There is nothing like square root there. I am going to put this equation together now so that you can see the overall relationship which you might be expected to memorize. So that when questions are given to you, you know the part of the formula that applies and then you use it to solve. Please watch the screen as the relationship displays. Okay? So we have the rate of diffusion of gas A divided by rate of diffusion of gas B equal to square root of density of gas B over density of gas A. And that is equal to square root of molecular weight of gas B over molecular weight of gas A. And that is equal to time of gas B over time of gas A. So that is the overall relationship I would like you to take note of. And the examiner also wants you to know this relationship. When questions are given to you, depending on the parameters mentioned, you will now know the part of this equation to extract and then use in solving that question. I hope you learned something from this video lesson. If you do, please hit the like button. If you are yet to subscribe to this channel, please do well to subscribe, where you get fundamental knowledge of maths, physics, chemistry, alright, at different levels of learning. In my next video lesson, I am going to release a calculation where I will apply this formula that has been derived already. You will not want to miss out in that class, so if you have not personalized the subscription, kindly do so. After subscribing, you will see an icon, a bell-like icon. Click on that bell and then, of course, click on personalize so that once I upload any new content, you will be personally notified. I'll be seeing you in my next video lesson. From JAMB 41, remember to always take your studies seriously.